Somewhere in the middle of the Pacific Ocean, right now, something is happening that should not be possible. Two forces that are supposed to be opposites, two climate personalities that cancel each other out by definition, are showing up in the same year, in the same ocean basin, almost close enough to touch. For decades, scientists told us El Niño and La Niña are a switch, on or off, warm or cold. You get one or you get the other, never both. But in 2025 and into 2026, the Pacific did something that made forecasters sit up and start double-checking their own data. A weak La Niña that had been quietly cooling the ocean surface began to collapse in a matter of weeks. And almost before the cold water had finished draining away, a new warm signal started rising underneath it, so fast that by the middle of 2026, meteorologists were using words like whiplash and flip, and even the phrase nobody wants to hear in climate science, unprecedented speed. So the question people keep typing into search bars is simple. Can El Niño and La Niña actually happen at the same time? And the honest answer is stranger than a plain yes or no. In the purest technical sense, the answer is no, they cannot coexist, because they are defined as opposite temperature states of the exact same patch of ocean. But if you stop there, you miss the real story, because the ocean does not care about clean definitions, it cares about physics. And in 2026, the physics produced something that looked, felt, and behaved almost exactly like both states overlapping, dragging global weather through a transition so violent that farmers, insurers, and disaster planners on 4 continents are still trying to catch up. To understand why this matters, you have to go back to what El Niño and La Niña actually are, stripped of the jargon. Picture a giant conveyor belt of wind blowing across the equatorial Pacific, from South America toward Asia. Normally those winds are strong and steady, and they drag warm surface water westward, piling it up near Indonesia, while cold water rises up from the deep near Peru and Ecuador to replace it. That is the baseline. That is normal. El Niño happens when those winds weaken or even reverse, and the warm water that was piled up in the west sloshes back east, spreading across the central and eastern Pacific like a hot blanket unrolling across thousands of kilometers of ocean. La Niña is the mirror image. The winds strengthen instead of weakening, the cold upwelling intensifies, and the eastern Pacific turns colder than usual, while the western Pacific gets even warmer and wetter. Together, scientists call this entire seesaw the El Niño Southern Oscillation, ENSO for short, and it is arguably the single most powerful natural driver of year-to-year weather on this planet. Here is the part almost nobody explains properly. ENSO is not actually 2 separate events. It is one continuous, oscillating system, constantly in motion, constantly leaning one way or the other, like a giant pendulum that never fully stops. Between the extremes sits a phase called ENSO neutral, where the ocean is close to its long-term average, and neither pattern is dominant. Climatologists at institutions like NOAA have quietly admitted for years that El Niño and La Niña are not 2 distinct boxes you tick. They are labels stapled onto a spectrum, which means the pendulum spends very little time sitting still and an enormous amount of time swinging through the messy, ambiguous middle ground, a zone where the signals genuinely can look mixed, contradictory, and confusing, even to the scientists reading the satellite data in real time. This is where the 2026 transition becomes so important, because it is one of the most dramatic examples of that messy middle ground playing out in front of a live global audience. At the start of the year, the tropical Pacific was locked in a weak La Niña. Sea surface temperatures in the benchmark Niño 3.4 region, the patch of ocean scientists watch most closely, were sitting around 0.5 degrees Celsius below normal. Trade winds were mildly enhanced. Rainfall was suppressed over the central Pacific and boosted over the far western Pacific and parts of Australia and Indonesia, the classic La Niña signature. By February, forecasters were already noting that this La Niña looked tired, weakening faster than models expected, with probability numbers shifting hard toward a neutral state within just a few months. Then, something unusual started building beneath the surface, literally. Long before the surface temperatures themselves shifted, a subsurface pool of warm water began pushing eastward from the western Pacific, riding along the thermocline, the boundary layer a couple hundred meters down, where warm surface water meets the colder, deep ocean. This subsurface warm pool is one of the classic fingerprints scientists use to spot an approaching El Niño months in advance, because it acts almost like a battery charging up before the visible discharge happens on the surface. By spring, that battery was charging fast. And by June, NOAA's Climate Prediction Center had done something it rarely does with this kind of speed. It upgraded the official alert status from an El Niño watch straight to an El Niño advisory, confirming that El Niño conditions were no longer just likely. They were already present, observed, real, measured in the water. By early August 2026, the weekly Niño 3.4 reading had rocketed to roughly plus 2.3 degrees Celsius, firmly inside strong El Niño territory. and the official 3-month average for the April through June period had already crossed the threshold that defines a full-blown episode. Forecasters were giving El Niño close to a 97 to 99% chance of persisting and intensifying through the coming winter, with a real possibility, something like 6 in 10 odds according to some model runs, that this event could grow into what meteorologists nervously call a super El Niño, a category reserved for only the most extreme episodes in the historical record, the kind that reshapes monsoon seasons, hurricane counts, and global temperature records for a year or more afterward. So within a single calendar year, the Pacific Ocean went from weak La Niña to declining La Niña to ENSO neutral to a rapidly strengthening El Niño potentially heading towards super status. That is not two opposite systems literally overlapping in the same weeks, but it is close enough, fast enough, and confusing enough that it explains exactly why so many people online are asking whether both patterns can exist together, because what they are actually sensing, correctly, is that the transition period between the two extremes can be genuinely chaotic, with signals from the outgoing pattern and the incoming pattern tangled together in the same season, sometimes even in the same week's satellite pass. There's also a second, quieter layer to this story that most headlines skip entirely, and it involves geography, not just timing. ENSO is not the only ocean oscillation running on this planet. The Indian Ocean has its own version, called the Indian Ocean Dipole, where the western Indian Ocean near Africa and the eastern Indian Ocean near Indonesia swing between warm and cool phases largely independent of what the Pacific is doing, although the two systems do influence each other. It is entirely possible, and has happened multiple times in recorded climate history, for the Pacific to be leaning toward El Niño while the Indian Ocean simultaneously sits in a negative dipole phase that behaves, in terms of regional rainfall and drought, almost like a La Niña signature for the countries bordering that ocean. From the ground, in a country like Kenya or a region like coastal Australia, this can genuinely feel like both patterns are punishing or blessing you at once, because the atmospheric teleconnections, the long invisible threads that link ocean temperature to rainfall thousands of kilometers away, are stacking on top of each other rather than canceling out. Then there is the concept scientists call ENSO Modoki, a Japanese term roughly meaning similar but different, first used seriously in climate research around the mid-2000s. A classic El Niño warms the eastern Pacific most strongly, right up against the coast of South America. A Modoki event instead warms the central Pacific most strongly, leaving the far eastern Pacific closer to normal or even slightly cool. Depending on which index you are watching and which region of the ocean you weight most heavily, it is genuinely possible for one dataset to flag weak El Niño conditions in the central Pacific, while another dataset, looking specifically at the eastern strip near Peru, still shows lingering cool anomalies left over from the previous La Niña. Neither reading is wrong. They are simply measuring different patches of an ocean that does not warm or cool uniformly, and in a fast transition year like 2026, those regional discontinuities become unusually visible. There's a third mechanism worth understanding, and it is one of the more elegant pieces of oceanography behind this entire phenomenon. La Niña does not vanish instantly the way a light switch turns off. It leaves behind what scientists sometimes describe as thermal inertia, heat and momentum stored in ocean currents and subsurface water masses that take months, sometimes over a year, to fully dissipate. Meanwhile, El Niño's own warm signal, once triggered by that eastward-moving subsurface pulse along the thermocline, can begin influencing atmospheric pressure patterns, jet stream positioning, and even Atlantic hurricane activity before the Pacific surface temperature has technically crossed the official threshold. So, for a window of real time, sometimes weeks, sometimes a few months, you can have El Niño's fingerprints appearing in the atmosphere while La Niña's fingerprints are still fading out of the ocean. Different mediums, different timescales, same overlapping window. That overlap is not a myth. It is a documented, physically real feature of ENSO transitions, and 2026 is turning into one of the sharper examples of it happening on record. Now, why does any of this actually matter to someone who has never looked at a sea surface temperature map in their life? Because ENSO's reach is almost absurdly long. A shift in ocean temperature across a strip of the Pacific barely a few degrees wide in latitude somehow ends up deciding whether farmers in India get a healthy monsoon or a drought, whether the American South gets a wet winter or a dry one, whether Atlantic hurricane season produces a dozen storms or barely half that many, and whether wildfire risk in Australia and Indonesia spikes into catastrophic territory. El Niño years have historically been associated with reduced Atlantic hurricane activity because the stronger upper-level winds that come with El Niño tend to shred developing storms before they can organize. They have also historically been associated with drought stress across Indonesia, the Philippines, southern Africa, and parts of India, alongside wetter than average conditions across the southern United States and parts of South America. La Niña tends to flip almost all of that, fueling more active Atlantic hurricane seasons, drier conditions across the American South, and typically wetter conditions across large parts of Australia and Southeast Asia. Now imagine trying to plan an agricultural season, an insurance model, or a disaster response budget when the system driving all of those outcomes just spent a single year sprinting from one extreme through the murky middle toward the opposite extreme, faster than most historical transitions on record. That is the real grounded version of the panic behind the clickbait question. It is not that two opposing ocean states are literally sitting on top of each other in the same water at the same moment. It is that the transition itself has become so rapid, so compressed, that forecasters, farmers, and governments are being forced to react to conditions that are shifting faster than their planning cycles can absorb. History gives us a few other case studies worth knowing, because 2026 is dramatic. But it is not entirely without precedent. The transition out of the powerful 1997-98 El Niño, one of the strongest ever recorded, flipped almost immediately into a multi-year La Niña, with barely any lingering neutral phase in between, catching climate models of that era badly off guard. Researchers studying that flip found that unusually strong El Niño events tend to recharge the ocean with so much subsurface cold water displaced toward the eastern Pacific that the system essentially overshoots straight into La Niña once the warm event collapses, like a pendulum swinging too far in the opposite direction after being pulled unusually high on one side. Some of the strongest El Niños in the historical record have been followed not by a gentle return to neutral, but by fast, sometimes multi-year La Niña episodes immediately afterward. And scientists studying these patterns have connected that overshoot directly to the amount of energy and subsurface water displacement the original El Niño generated. There is also a fascinating and still slightly controversial thread of research suggesting the switch itself, the actual mechanical trigger that flips the system from one phase to the other, may be connected to slow-moving subsurface ocean waves that propagate from the western Pacific toward the central and eastern Pacific over a period of months. Waves that some researchers have tied to the gravitational pull of the moon acting on ocean tides at a very deep, very gradual scale. The research remains debated within the broader climate science community, and it is not treated as settled fact, but it is a genuinely serious hypothesis published in peer-reviewed literature, and it hints at just how much about the exact mechanics of ENSO switching remains only partially understood, even after more than a century of observation dating back to the 1870s famine that first drew scientific attention to this cycle in the first place. What makes the current transition especially notable is not just its speed, but its scale. The jump from a weak, already fading La Niña at the start of 2026 to a strong, rapidly intensifying El Niño advisory by summer represents one of the more compressed full-cycle swings observed in recent decades. Sea surface temperature anomalies climbing above plus 2 degrees Celsius within months of sitting in negative territory is the kind of number that makes seasonal forecasters recheck their instruments before they trust the model output. And because El Niño's influence on global average temperature tends to peak roughly 6 to 9 months after the ocean signal itself peaks, meteorologists are already warning that if this event does reach super El Niño intensity later in the year, the knock-on effects, extreme heat records, disrupted monsoon timing, altered hurricane behavior, and shifted wildfire seasons across multiple continents will likely stretch well into 2027 before the system fully settles. To really feel the weight of what a fast ENSO flip does to the real world, it helps to walk through specific places rather than staying in the abstract language of anomalies and indices. Take the anchovy fisheries off the coast of Peru, an industry that quite literally built the modern understanding of El Niño, since the name itself was coined by local fishermen who noticed the warm current arriving around Christmas time, disrupting the cold, nutrient-rich upwelling that anchovy populations depend on to survive. When El Niño strengthens, that cold water retreats, the food web collapses locally, and an industry responsible for a meaningful share of the world's fish meal supply used to feed farmed fish and livestock across the planet can see catches fall by huge margins within a single season. A rapid, intensifying El Niño arriving in the second half of 2026 means Peruvian fishing communities are watching the same ocean signal that global meteorologists are tracking on satellite maps. Except for them, it translates directly into boats staying docked and household income disappearing. Move across to India, where the summer monsoon delivers something like 70% of the country's annual rainfall and underpins the livelihoods of hundreds of millions of farmers. El Niño years have historically correlated with weaker, more erratic monsoon rainfall, sometimes triggering serious drought stress across central and southern India, while La Niña years tend to favor a stronger, more reliable monsoon. A transition year, where La Niña conditions dominate the early monsoon months before El Niño takes over later in the season, creates exactly the kind of scheduling nightmare agricultural planners dread. Because sowing decisions made in June based on one climate signal can be undermined by a completely different signal taking hold by September, right as crops are approaching harvest. The same uncertainty ripples through commodity markets, where traders watching wheat, rice, and sugar futures treat ENSO updates almost like central bank announcements, because a shift in monsoon reliability can move global food prices within days of a forecast update. Australia tells a similar story from the opposite angle. La Niña years there typically bring above average rainfall and can ease drought and bushfire risk, while El Niño years are strongly associated with hotter, drier conditions and dramatically elevated wildfire danger, the kind of pattern that contributed to some of the country's most catastrophic fire seasons in recent memory. A rapid swing from La Niña into a potentially super-strength El Niño within a single year means fuel loads that built up during wetter months, extra grass, and vegetation growth, encouraged by the earlier rains, can dry out fast once the hot, dry El Niño pattern locks in, effectively loading the landscape with fire fuel before flipping the switch on the heat and dryness needed to ignite it. Fire authorities across southeastern Australia have openly flagged this exact sequence: wet start followed by hot, dry finish as one of the more dangerous setups for an intense fire season. Across the Atlantic Basin, hurricane forecasters watch ENSO with almost as much attention as sea surface temperatures in the tropical Atlantic itself, because wind shear driven by El Niño tends to tear apart developing storms before they can strengthen, while La Niña's weaker upper-level winds tend to let storms organize more easily and intensify further. A hurricane season that begins under lingering La Niña influence and then transitions into a strengthening El Niño partway through can produce a strange split personality, an active, storm-friendly, start followed by a sudden fall-off in activity as the wind shear increases, catching forecasters and coastal communities in a genuinely difficult position when it comes to timing, evacuation planning, and insurance risk models that were built around a single, a stable seasonal outlook rather than a moving target. Insurance and reinsurance companies, the giant financial institutions that ultimately absorb much of the economic damage from these climate swings, have become some of the most sophisticated consumers of ENSO forecasting in the world, not out of scientific curiosity, but out of financial necessity. A rapidly intensifying El Niño reshapes flood risk maps across South America, drought risk models across southern Africa and Australia, and wildfire exposure calculations across the western United States and Australia almost simultaneously. When the transition itself becomes unusually fast, as it has in 2026, the actuarial models built on decades of slower, more gradual historical transitions can lag behind reality, forcing rapid recalibration in the middle of a policy year, an unglamorous but genuinely consequential ripple effect of ocean temperatures shifting a few degrees over a few months. Even global average surface temperature, the headline number used to track the pace of overall planetary warming, gets tangled up in this story. El Niño events tend to release stored ocean heat into the atmosphere, temporarily pushing global average temperatures higher on top of the underlying long-term warming trend, while La Niña tends to bury heat below the surface and can temporarily suppress that same global average reading. A year that swings from La Niña toward a strong or super El Niño is a year where climate scientists widely expect global temperature records to come under serious pressure, not because the swing itself represents new warming, but because it unmasks heat that had been hidden below the ocean surface during the preceding cooler phase. Researchers at climate monitoring agencies have been explicit that this kind of natural internal variability, layered on top of the human-driven warming trend, is exactly why some years break records dramatically while others plateau, even though the underlying trend line keeps climbing steadily beneath the noise. It is worth being honest about what remains uncertain here too, because overselling the drama would be its own kind of dishonesty. Forecasting the exact peak intensity of an ENSO event, especially one still actively strengthening, is genuinely one of the hardest problems in climate science. And even confident model agreement in August can shift by winter. Some ENSO events that looked destined to become historically extreme have stalled out at moderate intensity. And some quiet, unremarkable starts have surged unexpectedly late in the season. The subsurface warm pool currently feeding this event is real and measured, not projected, which gives forecasters unusually high confidence for this stage of the year, but the exact trajectory from here, whether this becomes a full super El Niño or plateaus at a strong but more moderate level, is still being written in real time by ocean dynamics too complex for any single model to fully capture. There is also a forecasting story hiding underneath all of this, one about how much the tools themselves have changed. 3 decades ago, catching an ENSO transition this early, while the driving signal was still a subsurface pulse of warm water hundreds of meters below a calm-looking surface, would have been close to impossible. The current generation of ocean monitoring relies on a network of moored and drifting buoys scattered across the tropical Pacific, satellite altimetry capable of detecting sea surface height changes of only a few centimeters, and coupled ocean-atmosphere computer models that run repeatedly through slightly varied starting conditions to generate a spread of possible futures rather than a single rigid prediction. That is why forecasters in 2026 were able to flag the shift from La Niña toward El Niño months before it was obvious to anyone simply checking whether the weather felt different outside. The subsurface warm pool was detected, tracked, and modeled forward before it ever reached the surface, which is precisely why the alert status moved from watch to advisory with unusual speed and unusual confidence for this stage of an event's life cycle. That improved lead time matters enormously in practice, because it changes what governments and industries can actually do about an incoming climate shift, rather than simply reacting after the fact. Agricultural ministries in vulnerable regions can adjust planting recommendations before the rains fail. Disaster management agencies can pre-position resources ahead of an anticipated wildfire season rather than scrambling once fires are already burning. Central banks and food security analysts can factor a shifting ENSO outlook into inflation forecasts for commodities like wheat, palm oil, and sugar, all of which are sensitive to Pacific-driven rainfall patterns in producing countries. None of this eliminates the disruption caused by a fast, sharp transition like the one currently unfolding. But it does compress the gap between the ocean's behavior and the world's ability to respond to it, turning what used to be a purely reactive relationship into something closer to genuine early warning. None of this erases the genuine scientific humility still required here either. Even with better buoys, better satellites, and better models, ENSO remains famously resistant to precise long-range prediction, something researchers have openly called one of the most persistent unsolved problems in seasonal climate science. Part of the difficulty is that the system is chaotic in the mathematical sense, meaning tiny differences in starting conditions can cascade into meaningfully different outcomes months later, the same underlying unpredictability that limits weather, forecasting itself, just operating on a slower oceanic timescale instead of a daily atmospheric one. Part of the difficulty is that ENSO does not operate in isolation, and its interactions with the Indian Ocean Dipole, the Atlantic meridional mode, and even Arctic sea ice patterns are still active areas of research rather than settled, fully quantified relationships. And part of the difficulty, as that subsurface lunar tidal research hints at, is that we may still be missing pieces of the fundamental mechanical trigger that decides exactly when and how forcefully the system flips from one phase to the other. What all of this adds up to is a much richer, much more honest answer than the clickbait version of the question ever could have given. El Niño and La Niña are not, and cannot be, literally active in the exact same patch of ocean at the exact same moment, because they are opposite temperature states of that same region by definition. And physics does not allow a single body of water to be simultaneously warmer and colder than average in the same breath. But the spirit of the question, the sense that something contradictory and overlapping is happening right now in the Pacific, is not a myth born out of internet confusion. It is a reasonably accurate read of a genuinely strange transitional year, one where a fading La Niña's lingering effects tangled with a rapidly strengthening El Niño's earliest atmospheric fingerprints, where different ocean basins told different regional stories at the same time, where subsurface signals moved faster than surface temperatures could keep up with, and where the compressed timeline of the entire flip left very little room for the usual, gentler drift through a long, calm, neutral phase that textbooks tend to describe. What is not uncertain is the underlying lesson buried inside this entire episode. The question of whether El Niño and La Niña can happen at the same time turns out to be less about literal simultaneity and more about how badly our simple mental categories fail to capture a system this fluid. The ocean does not experience seasons the way a calendar does. It carries momentum from one state into the next. It warms and cools unevenly across different basins and different depths. It interacts with sibling systems in the Indian and Atlantic Oceans that can amplify or contradict its own signal. And it can pivot from one extreme toward another faster than the institutions built to track it can fully update their language. What people are really noticing when they ask this question is that the boundary between El Niño and La Niña was never as clean as the diagrams and textbooks suggested. It is a boundary that blurs, overlaps, and occasionally sprints across itself within a single calendar year. And 2026 may end up remembered as one of the clearest examples of exactly that happening on a global stage, with consequences for harvests, storms, and heat records that are still unfolding as this very transition continues to strengthen beneath the surface of an ocean most people will never see.